So, welcome to lecture series. Today, we will discuss about the algebra or linear transformations. That is, let V and W be two vector spaces defined over a field, say capital F. If we consider T and U to linear transformation from V into W. Then if I define a sum functions, define addition and I can say multiplication or scalar multiplication as T plus U operating on any vector alpha which belongs to V as T of alpha plus U of alpha for alpha belongs to V. Any C belongs to your F, C T alpha I am defining as C T of alpha. Okay, this is my some sort of scalar multiplication please. Basically, if you consider V and W as a two different set and if you consider the functions from V to W and if you collect all the functions from V to W defined by like addition like 1 and scalar multiplication 2, we have seen that is vector space. But here I am not talking T and U is any functions, I am saying that T and U are a linear transformation from V to W and we have defined sum of two linear transformation T and U as T plus U of alpha equal to T alpha plus U alpha, and for any C belongs to capital F, C T alpha is equal to C of T alpha please. Then claim T plus U is also a function from V into W and also linear transformation. Similarly, Ct is also a function of V from this and also linear transformation please. If I can somehow prove it, then if I collect all the linear transformation from V to W and if I denote that set is suppose LVW, then we have to show that I will basically show that LVW is also a vector space. I am coming to that once, but before that let me see whether the way I have defined 1 and 2, whether T plus U is a linear transformation from V to W or not and Ct is also linear transformation from V to W or not. Let us quickly check that one first. For linear transformation we have to consider, so consider alpha beta belongs to V, P any two elements and okay, say D belongs to capital F, B any scalar. Then d alpha plus beta belongs to capital V, and we have t plus u of d alpha plus beta equal to t of d alpha plus beta plus u of d alpha plus beta, and this is equal to d of t alpha plus t beta plus d of u alpha plus u beta, because t and u are linear transformation from V to W, the definition I have used. So, this means that t plus u of this d alpha plus beta is equal to, I can write down d times t of alpha plus u of alpha plus t of beta plus u of beta. This is equal to d times t of t plus u of alpha plus t plus u times of beta, please. I wrote basically t plus u of d alpha plus beta equal to, so d times t plus u of alpha plus t plus u of beta, please. So, this implies t plus u is a linear transformation from V into W. Again, immediately one can check Ct of d alpha plus beta, also similar way I will have C of t of d alpha plus beta, which is equal to C times d times t of alpha plus t of beta. So, this means that this is equal to Ct of, I can d taken out, Ct of alpha plus Ct, okay, C is there, Ct of beta, please. So, this means that Ct is also linear transformation from V into W, it is fine. So, we have seen that if T is a linear transformation from V to W and U is also linear transformation from V to W, then T plus U is also linear transformation from V to W, and C times T also linear transformation from V to W. Now, consider L V W as collection of all linear transformation from V into W. Consider for any T and U belongs to LVW, T plus U of alpha equal to T of alpha plus U of alpha, and Ct of alpha equal to C of T alpha. Okay. For all alpha belongs to V, for any C belongs to F. That is basically the V and W are defined over the field capital F that I have considered. Then LVW is a vector space, Now, to prove it is a vector space, I have to prove all the axioms of the vector space I mean to say, I have to show that LVW is an abelian group with respect to addition, which is defined like 1, and it satisfied 5 more axioms with respect to scalar multiplication defined as 2. Okay. Here that 0 transformations V2W is basically 0 element of this set LVW, please. So, the way it has been defined, we see that the LVW is a closed with respect to additions, and another important thing is there, you see, we have already seen, if I consider the collection of all functions from a set V to another set W defined by say f1 plus f2 of s is equal to f1 of s plus f2 s, and c time f1 of s is equal to c of f1 s. So, with respect to that type of vector addition and scalar multiplication, your set of all the functions from V to W will be a vector space. Now, my collection LVW here is basically collection of all linear transformations. This is also function, but it is special characteristics. It is having special nature. What is that? That for each function belongs to LVW, it is basically linear transformation, please. So, this will be a subset of the vector space consisting of all the function from V to W, please. You have to show that that set of all this linear transformation, all the function which is basically function of linear transformation will be a subspace of that set, please. One can think that way, but without going that side also, one can again prove independently that LVW is a vector space. Closure property holds good with respect to addition, that is from the definition itself already seen. Associativity property will also holds good because we have already seen the set of function from a set V to W satisfied associative property. So, that associative nature will also holds good for this special kind of function, that is linear transformation also. Next point will be the question of existence of 0 element. 0 element is basically 0 transformations, linear transformation. So, that is also there. Next will be the additive inverse. So, for any linear transformation T from V to W, one can again define minus T from V to W, so that T plus minus T will be 0 transformation, please. So, that is also there. And commutative property holds good because here the T alpha or U alpha, see, this is are element of the vector space which is also satisfied commutative property, please. So, T plus U of alpha, which is equal to T alpha plus U alpha, one can write down again U alpha plus T alpha also, because these are the elements in the vector space W. So, which satisfied the commutative property. So, therefore, it satisfied all these axioms of the abelian characteristic of the space LVW with respect to addition. Similarly, one can check 5 more axioms with respect to scalar multiplications. So, I am leaving it as a homework for you. Please, you can check it that LVW is a vector space with respect to the binary operation, that is vector addition defined as 1 and scalar multiplication defined as 2. Let me see, can I give some dimension for the LVW? Let V and W be two finite dimensional vector spaces defined over the field F. Let dimension of V equal to n and dimension of W equal to m. Then dimension of LVW is Mn. So, we have picked up questions that say it is like this: V and W be two finite dimensional vector spaces over the field capital F, and dimension of V is equal to say n, and dimension of W is say small m. Then dimension of LVW is Mn. So, you can say this is theorems. Now, to prove the above results, we have to construct Mn elements of LVW which will span LVW and linearly independent also. So, let B equal to alpha 1, alpha 2, alpha n, and B star equal to beta 1, beta 2 and beta m be order basis of V and W respectively. So, I have considered order basis for V, order basis for W first. Now, I have to construct Mn functions from V to W. Now, for each pair of integer PQ where 1 less than equal to P less than equal to M and 1 less than equal to Q less than equal to N, consider a function, you consider a function EPQ V to W defined by that every alpha j, basically EPQ of alpha j goes to, it will be 0 if j not equal to Q, j not equal to Q, and this will be equal to beta P if j equal to Q. So, when j equal to Q, I am writing EPQ of alpha j equal to beta P. So, this means what? This is equal to Kronecker delta JQ beta P. I mean delta JQ means when j is equal to Q, it is equal to 1 and other is 0. So, EPQ is a linear transformation from V into W. How? How can I say that EPQ is a linear transformation from V into W? The reason is we have already seen in the existence of linear transformation from a vector space V to W for a given order basis. If you consider same number of elements in the corresponding W space, then there exists a unique linear transformation which will map to alpha j to beta j type. So, if I consider here the set is basically your alpha 1, alpha 2, alpha n, this is one set basically order basis in B, and other set is basically I am saying that this is your 0, 0, beta p at qth place please, then 0 and 0 please. So, this is a subset of W, this is subset of V, this subset is linearly independent. We know there is a unique linear transformation which is mapping alpha I to this set please. I mean if I consider this is say gamma 1, gamma 2, gamma n, then there is a linear transformation mapping alpha 1 to gamma 1, alpha 2 to gamma 2 like that. So, based on that philosophy I can say that here EPQ, the way it is defined from V to W is a linear transformation. Since this is a order basis, this of V and n elements of W, and this function is basically mapping between these two sets, and so EPQ is a linear transformation from V into W. So, this is true for any order pair PQ when 1 less than or equal to P less than or equal to M and 1 less than or equal to Q less than or equal to N. So, there are Mn functions of the form of EPQ from V into W. I will say this is a linear transformation please. There are Mn linear transformation EPQ from V to W. Claim this EPQ 1 less than or equal to P less than or equal to M and 1 less than or equal to Q less than or equal to N spans LVW. Let T be a linear transformation from V into W. I have considered any arbitrary linear transformation T from V into W. I mean to say T is an arbitrary element of LVW, that is T belongs to LVW. My claim is that T can be written as linear combinations of this Mn linear transformation please. Okay. For alpha j belongs to V, this alpha j is basically basis element of the V please. Now, T alpha j will belongs to W. So, this means that I will be able to express T alpha j as a linear combination of the basis element W, means there exist M constants. So, just M scalars say Aij I equal to 1 to M belongs to capital F such that your T of alpha j equal to sigma A I j beta I equal to 1 to M. So, I will have like this thing please. So, for any fictive T as alpha j I have picked up from the set of order basis basically of the V, and we have written T alpha j as like this thing please. Claim T equal to like this, something like P equal to 1 to M, Q equal to 1 to N, APQ and EPQ. Claim T is basically linear combinations of this PQ linear transformation please, with the coefficient is here APQ type. Let U is equal to, say, let it is not T, it is equal to some linear transformation from V into W, let me give the name as capital U. So, capital U is equal to, say, P equal to 1 to M and Q equal to 1 to N APQ and EPQ. So, now if I see the image of alpha j under U, now U of alpha j will be equal to what? This will be equal to P equal to 1 to M and Q equal to 1 to N APQ EPQ operating on alpha j. Okay, already we know the definition of EPQ. We know EPQ operating on alpha j equal to delta jq into beta p. So, U alpha j equal to like this is equal to sigma p equal to 1 to m sigma q equal to 1 to n, will have APQ and delta jq into beta p. So, this means that this is equal to simply p equal to 1 to m when j equal to q. So, it will be A pj and beta p. So, this is equal to, if I see this definition of T and here also I am getting same. So, this is equal to, I can say, T of alpha j. So, this implies T equal to U equal to sigma P equal to 1 to m and Q is equal to 1 to n APQ and EPQ. I have shown that any linear transformation from V into W can be written as a linear combination of these Mn linear transformations. Now, I have to show that this Mn linear transformation EPQ is linearly independent. Now, I have to show that linearly independent Li of set of EPQ. Okay, so I have to prove this one please. See, the way we have written here, say T is equal to sigma P equal to 1 to M, Q equal to 1 to N, APQ and EPQ please. So, now for sigma P equal to 1 to M and Q equal to 1 to N, if I write down for any linear combinations like say APQ and EPQ, and suppose this is equal to 0, if I do it, this means it is 0 linear transformation. So, this means sigma APQ EPQ P equal to 1 to M and Q equal to 1 to N when it is operating on say alpha j. This is I am getting equal to 0 for all alpha j, for all alpha j belongs to the basis element B please. So, this for particular j alpha j I am getting what? This is equal to sigma P equal to 1 to M sigma APQ and EPQ operating on alpha j, that is equal to, we know this is equal to beta p into delta qj, delta qj. So, this is equal to sigma APJ beta p. p equal to 1 to m, this is equal to 0. This implies APJ equal to 0 for p equal to 1 to m. Since beta 1, beta 2 and beta p is a linearly independent set of W. So, see that APJ equal to 0. This we have seen for any arbitrary j. So, this implies that if I take a linear combination of the EPQ, then that is equal to 0, means all the coefficients are equal to 0. So, EPQ 1 less than equal to p less than equal to m and 1 less than equal to q less than equal to n is linearly independent. So, it is a basis of LVW, please. So, we have seen that for the vector space LVW, when V and W is a finite dimensional of dimension n and m respectively, then the dimension of the vector space LVW, it will be finite and it is equal to Mn. And one can immediately easily, for a given order basis, one can easily construct the basis element also by this way, please. So, we will continue in the next class. Today that is all. Thank you.